Hi, I'm Bob Doyle, the information philosopher, webcasting from my ITV studio in Cambridge, Massachusetts. I'm hoping to reach philosophers and scientists around the world to help solve several problems in philosophy, in physics, in biology, and in psychology. I also hope to reach any of you wondering about the deepest nature of reality and our place in the universe. We live in the information age, but I find that very few philosophers or scientists understand the nature of information. Information is neither matter nor energy. Information needs matter to be embodied in our brains, for example. And it needs energy to be communicated, like this lecture coming to you over the internet. But matter and energy are conserved quantities. It may be hard to believe, but the total amount of matter and energy in the universe today is the same as there was at the beginning of the universe nearly 14 billion years ago. And if the stuff of the material world is just a fixed total amount, then what can possibly explain all the evolutionary change we see around us? These changes are the information and order in the universe, which I'm going to show has been increasing since the beginning of time, despite the second law of thermodynamics, where entropy tends to destroy order. So change is simply the arrangement of the existing atoms and molecules into what I call information structures, like the galaxies, stars, and planets. But stars and planets are passive objects under the complete control of physical forces like gravity, chemical forces, nuclear forces, and so forth. On the other hand, living things, you and I, are dynamic and growing information structures and under our own control. I'll show that we are forms through which matter and energy are continuously flowing, and I'll show its information processing from the DNA in our cells to the thinking in our minds that controls these flows of matter and energy. Information is the modern spirit, the ghost in the machine, the mind in the body. It's our souls, and when we die, it's our information that perishes. Only our matter remains. Okay, today's Monday, the beginning of our 4th week of online lectures on YouTube and Facebook and over our local public access cable station in Cambridge, CCTV. So Mondays we're normally spending on discussions of our great problems in philosophy and physics. And the problem I'd like to turn to today is one we've touched on quite a bit already. It's called the collapse of the wave function. And this very complicated problem, see if I can zoom in a little bit on us. Here we go. It's called the probability amplitude wave function. And it collapses during a measurement. And this collapse, understanding the collapse, is without a doubt the most controversial problem in physics today. Of the several interpretations of quantum mechanics, more than half of them deny this collapse of the wave function. Some of them even deny what are called quantum jumps and even the existence of concrete particles. So I'm going to show today that understanding the great problems, the great problem of the collapsing wave function, is best understood with two very strongly related questions or problems. One is the relationship between the wave part of the wave function, which collapses, and the particle part, which is what we have after the so-called collapse of the wave function. Now, the most important experiment that exhibits this very strange process of waves everywhere, followed by the appearance of a single particle in one location, is called the TwoSlit experiment. And that TwoSlit experiment is almost always taught as something that it cannot be understood. And Richard Feynman, the great quantum physicist, argued that the two-slit experiment really contains the very most pressing, or indeed the only mystery in quantum mechanics. And he argued that any other of the strange things that are thought of as quantum phenomena, mysterious phenomena going on down at quantum reality, can be thought about, analyzed in terms of the two-slit experiment. Let me bring this screen up, see if I can take a look at this with you for a moment. You'll see here that Feynman says, I can take just this one experiment, which has been designed to contain all of the mystery of quantum mechanics, to put you up against the paradoxes and the mysteries and the peculiarities of nature 100%. And then he claims, any other situation in quantum mechanics, it turns out, can always be explained by saying, you remember that case of the experiment with the two holes? It's the same thing. So our hope is to go through some of the best descriptions of this two-hole experiment. Feynman called it two-slit experiment, better known as, and get a deep feeling for what people are trying to tell us is going on. Now, I've looked at dozens of books on quantum mechanics, almost all of which describe this very mysterious experiment. I've looked at a huge number of YouTube videos recently. And so one of the things I'm going to focus on today is what I regard as the very best animations that are presently on YouTube on the two-slit experiment. Here you see I'm trying to use my hashtags, so I say hashtag two-slit, one word. In the future, maybe my use of these hashtags will help people come back and find what we're doing together here to try to understand two-slit experiment and the difference between waves and particles that it shows, and ultimately how we can see what it means when the wave function collapses. Because there is a kind of a dramatic change in the wave function, which unfortunately has been associated with the word collapse. It turns out that our word collapse generally means something starts very large and it winds up collapsing. And indeed, after the collapse, we have a single particle at a single point. Whereas before that, we have the wave spread out over a large amount of space, extremely large in some cases. So that does fit the picture of a collapse. It's just that there's a basic problem here. The wave function itself is immaterial. Now, you know, if you've been watching my lectures, I call myself the information philosopher because I regard information as an abstract thing. For example, a mathematical function, which is what the wave function is. It's something that has values, and those values depend on the various points in space. The value of the wave function is large here, small there, zero here, and so forth. It's just a function. It is a form of knowledge in the head in the head of a physicist who calculates this wave function using an equation Erwin Schrödinger discovered that describes waves. It's a slight variation on the equation that describes water waves, so there's always been a great similarity between water and light waves, these quantum waves. And we'll explore that some and why it is. A lot of people feel that it can be explained if we just think about what's going on with light waves. But light waves and water waves both contain things. Water contains water molecules. Water waves contain water molecules. Light waves contain packets of energy, we now know, which were originally discovered by Albert Einstein. He called them light quanta. And that is the quantum of quantum theory. Later they were known as photons. So a light wave contains a lot of stuff. It contains a lot of photons. But a probability wave is totally unlike either of those. Those contain substance, energy in the one case, material in the other. But the probability wave contains nothing concrete. It's just an abstract quantity which gives us something, and thus the value of this wave function. Einstein was the first to see and say that it gives us the probability of finding a particle, whether that's a particle of light, in his case of his light quanta, or later on a particle like an electron, or in general, what quantum mechanics does is calculate the wave function and based on the wave function make predictions about where we are going to find the thing being described by the wave function. If it's a wave function for an electron, it tells us the probability that there will be an electron in different places. In order to evaluate whether that probability calculation is good, whether it makes a good prediction, whether quantum physics is a good theory, we have to do experiments. And the relationship between the one wave function, which makes the theoretical prediction, and the experiments, which have to be many in order to verify the predictions, is the same as the relationship, in a way, between ideal things and material things. Because our predictions, our theories, are just ideas, and our experiments, where we actually measure and find material objects like electrons in various places, is concrete. So, what is this connection between the ideal and the material, as I put it, or pure information, abstract information, and concrete objects? That's said to be shown to us best by this two-slit experiment. So let me go here to the screen I have behind us and just take a look at what I'm saying. I've actually just got 3 important videos I'd like to show you, and what they're going to try to show us is the kind of thing we get when we have a slit, and here in this picture there's a little slit at the bottom, and waves are going through. Those waves fan out in all directions, and there's a certain amount of interference between the different waves which are coming. Even though there's just one slit, there's a certain interaction between the waves that come off one side of the slit and those that come off the other side of the slit. So let me go back to this picture for a moment and show you that. Let's expand this fellow so we can see it a little bit better. Show you what I'm doing here. Take a quick look over and see that what I've got here is my switcher, as usual, switching between scenes. And on this screen here I have my expanding and contracting image, which shows up on the screen behind us when I look at this. So this is my tool set. Give me a kind of a blackboard, but it's actually a computer-generated set of images that are playing on my website. This page on the website, so you can appreciate that, is, let's see if I can do that here. It's called Solutions Experiments Two-Slit Experiment. I should probably get a big copy of that out for you. But here we look, and we see that the rays of light coming through a single slit, just as if you sent water through this single slit, you would see it produces waves which interfere with one another, and there are these sort of beams, almost like beams of light, but in this case, this could be light, it could be water, it could be sound waves. They all have this phenomenon of interfering with one another. And generally what happens is most of the energy that goes through a slit goes right to the back wall, and this could be a wall measuring waves of water hitting, or it could be a screen which is detecting photons or light quanta landing on the screen with a CCD or a photographic plate measuring the number of particles of light that land here. And you see that there are areas where there's what's called destructive interference, and there's areas where there's constructive interference. Not sure how easy that is to read. Let me magnify it a little bit, bring it down. You see that at the areas where the beam-like fanning out of white area corresponds to constructive interference, where the one wave and the other wave are in phase with one another. In the middle, one wave has its height, crest it's called, of the wave, coinciding with the trough of the other wave, and they tend to cancel out, and those are the dark areas here. So let's go down below and take a look now at what happens when we have, instead of just one slit, where we have two slits. And this is the famous double slit interference pattern. Once again, we see now I've got two big holes, as Richard Feynman called them in his experiment, but we have the same overlapping of waves, but now instead of three, as we saw those beams-like things fanning out, we now see there are quite a few of them. 1, 2, 3, 4, and although those are faint off to the side, the ones in the middle, we have 5 fairly clear maxima instead of just one maximum. And so, because we now have two slits, we now have these interference fringes, they're called, multiple of them in the background. Now, it seems clear what's going on when it's water, because we've got energy coming through this side and through that side, and it's interfering with itself. But the puzzle in the two-slit experiment, the great difficulty in really expecting this as something intuitive, when it is so non-intuitive when looked at very closely, is that this experiment can be done with particles like electrons, material particles, or with light, photons. And this experiment can be done and shown even with a single particle of light or matter going through the experiment at one time. We turn down the amount of light and we see this same phenomenon of interference. Okay, so that's the background, and how it is that we're going to explain this. I'd like to take you to a video by the one we used a few days ago by an outfit called Veritasium. The founder of Veritasium is a very clever lecturer, science lecturer named Derek Muller. And I've just been enjoying many of his other pieces of work, but I want to show you a second one, much like the one we showed the other day, in which he talked a little bit about interference. Let me bring this up to the screen here. Actually, I can start it to play, and maybe I need to turn the sound up a little bit so we can hear him very well. Let's try this.
Has changed over the centuries. In the late 1600s, Huygens proposed that light was a type of wave, while Newton considered it a stream of particles. This debate appeared to be settled in 1801 by Young's double-slit experiment, which showed light passing through two slits produced patterns like water waves. But by 1900 it was clear that light energy was not evenly distributed as expected for a wave. Rather, on the smallest scales, it comes in lumps called quanta or photons. So the question is, how does this affect the double-slit experiment? Here I have a more contained double-slit experiment where there is a laser which fires a beam through a single slit, then through a double slit, and onto a screen where you can see a well-defined light comes. The sunlight.
Sorry, I
double-slit experiment where there is a laser which fires a beam through a single slit, then through a double slit, and onto a screen where you can see a well-defined interference pattern. There's a series of bright and dark bands which are much easier to observe than when I use sunlight, because with only one wavelength there are no other colors involved. This is what a graph of intensity versus position would look like for the interference pattern.
So we see there, let me bring this up on the screen behind me, just exactly what I showed you a moment ago with my multiple maxima, or peaks and valleys, places where there is light and places where there is no light, coming out when he's sending a beam of photons into this screen. So let's turn it on again.
Creates that pattern. Consider the bright spot in the middle. The light from each slit has to travel the same distance to reach that point, and hence both waves arrive in phase. That means crests with crests and troughs with troughs. So they add together and create an interference maximum, a bright spot. But if you look slightly to the left, there's a dark spot. Now that's because light from one slit has to travel on an angle, and it has to travel an extra half a wavelength compared to the light from the other slit. Which means when this light is arriving as a crest, the light from the other slit is arriving as a trough. And so they cancel each other out. But if you go further left, you see another bright spot, because now the light from one of the slits has to travel a full extra wavelength compared to the light from the other slit, and so again they arrive in phase, crests with crests and troughs with troughs, creating constructive interference, and so we see a bright spot of light. And that's how the whole pattern is created. But what if I decrease the intensity so much that there wasn't a whole wave of light going through there, there were only single photons? Then how could they interfere with each other because there's only one in the device at any one time? So would we still see an interference pattern? That is what we're going to find out. In order to make this work, I had to line up a very faint source, and to see where the light was going, I had to shroud my head in that black cloth. But I finally have the apparatus ready. You can see up here I have a frequency counter which actually counts the number of photons received per second at the detector. The detector is a photomultiplier tube, which is capable of detecting single photons. It's like a very sensitive eye, like the frog's eye. Now right now there's no light passing through to the detector, but there is still a bit of a background reading, and that's because I can't block all the light out of there. Plus there are cosmic rays passing through this room which will also set off the detector. I'm plotting a graph of the number of photons counted as a function of position across the detector. If you have a look after 1 second, the distribution seems random. There doesn't seem to be any pattern in the arrangement of those photons as they hit the detector. So maybe it's true. A single photon can't interfere with itself because it's just a localized point. It has to go through one slit or the other. But just to be sure, let's add up the results over a period of time and see if any pattern emerges. Look at that. You can clearly see the same interference pattern that we got when we were sending tons of photons through, but we're getting it out of single photons. We're counting up individual photons. And that pattern is emerging as we aggregate the results over time. But how could this be happening? How could a single photon pass through both slits? Well, if we try to interpret these results in terms of the objects we experience every day, they don't make any sense. A photon is something different to a macroscopic object. It's not a wave and it's not a particle, it's a quantum mechanical object. And sometimes it seems like it has properties of a wave, and sometimes it seems like it has properties of a particle, but ultimately it is something totally different to anything we've experienced before. And that's what makes this seem so counterintuitive. So what is light? Wave or particle? The true answer, I think, is neither. Though if you want, you could call it a wavicle.
Okay, that's a very popular way of describing the two-slit experiment, that what it shows is that whatever's going through has both wave and particle properties. And we want to say that it does have those properties, but the wave property is quite different from the material property. The wave property is information about probabilities where particles will be found. The particle is the material that we do find. But the puzzle remains, as he puts it, if we send one particle at a time, how can it be that it interferes with itself? Because it would appear, in order to interfere, it has to go through both slits, so as to have knowledge of the two slits affecting its behavior. So let's take a look at another lecture here, a little presentation. This one is from, let's see, the original double slit experiment, the quantum experiment. This one is called the quantum reality, the quantum experiment that broke reality. And let's take it to full screen. Let's first make sure I turn on the closed captions. Take it to full screen. And this is from PBS Digital Studios, a program called Space-Time. Let's watch this one.
Experiment. It's one of the most stunning illustrations of how the quantum world is very, very different from the large-scale world of our physical intuition. In fact, it hints that the fundamental nature of reality may not be physical at all, at least in any sense that we're familiar with.
Well, for some reason...
Let's start.
Some reason we're not seeing... For some reason we have nothing but a black screen, typical of my technical difficulties. Let's go back again and see if we can get this thing to start properly. There we are. I'll just refresh the whole screen, see if that helps.
This episode is supported by the great courses around 7.5%.
Oh, well, there's a picture. Let's see what we can do with this one.
It bobs up and down in a pool, causing periodic ripples to spread out. Some distance away, those waves encounter a barrier.
No luck.
Let's start with the familiar. In fact, let's start with the familiar. In fact, let's start with a rubber ducky. The world of our physical not be physical at all, at least in any sense that we're familiar with.
Close the page. That's unfortunate. Let's see if I can find it on another machine here. I'll go to this one, which has got our diagram on it, and I'll just open up a page here, go to youtube.com, and now this is, of course, what I hope you will be able to do. Let me put this up on my other screen so you can see what I'm doing. And I'll do this. So you see I'm basically entering youtube.com. And then we'll go to TwoSlit. And as I mentioned, there are a very large number of these TwoSlit studies. And let's see if we can find the one we want, see if it will play better for us here. Here's Dr. Quantum. You can't quite see that. Let me go here. The Dr. Quantum experiment we looked at the other day. This is the one I'm after, the quantum experiment that broke reality. And let's see.
This episode is supported by the Great Courses Plus.
This looks much better.
One of the strangest experimental results ever observed.
Let me just open him up and present this way.
Has got to be that of the single particle double slit experiment. It's one of the most stunning illustrations of how the quantum world is very, very different from the large-scale world of our physical intuition. In fact, it hints that the fundamental nature of reality may not be physical at all, at least in any sense that we're familiar with. Let's start with the familiar. In fact, let's start with a rubber ducky. It bobs up and down in a pool, causing periodic ripples to spread out. Some distance away, those waves encounter a barrier with two gaps cut in it. Most of the wave is blocked, but ripples pass through the gaps. When the new ripples...
Let me just point out here that we see the same kind of diagram that I've done with my little waves, and you see some places they are in phase with one another and they're creating what now looks like dark in this diagram, and then they're out of phase with one another and they interfere and produce no energy moving out. They're very nice animation. Let's start him again.
Start to overlap each other, they produce this really cool pattern. It's called an interference pattern. It's due to the fact that in some places the peak of the ripple from one gap stacks on top of the peak from the other gap, making a more extreme peak. You also get more extreme dips when two troughs overlap. We call this constructive interference. But when the peak from one wave encounters the trough from another, they cancel out, leaving nothing. Destructive interference. So we have these alternating tracks of wavy and flat water. Any type of wave should make an interference pattern like this. For example, water waves and sound waves, but also light waves. This double-slit interference of light was first observed by Thomas Young back in 1801. A source of light passing through two very thin slits produces bands of light and dark stripes, alternating regions of constructive and destructive interference on a screen. Of course, we now know that light is a wave in the electromagnetic field, thanks to the work of James Clerk Maxwell a century later. So it makes perfect sense that it should produce an interference pattern, right? But wait, we also know that light comes in indivisible little bundles of electromagnetic energy called photons. Einstein demonstrated this through the photoelectric effect, but his clue came from the quantized energy levels of Max Planck's blackbody radiation law. Check out our episode on this for the details. Okay, so each photon is a little bundle of waves of electromagnetic field, and each bundle can't be broken into smaller parts. That means that each photon should have to decide whether it's going to go through one slit or the other. It can't split in half and then recombine on the other side. That shouldn't be a problem as long as you have at least two photons. One photon passes through each slit, and then the two photons interact with each other on the other side and produce our interference pattern. But here, we get to one of the craziest experimental results in all of physics. The interference pattern is seen even if you fire those photons one at a time. Well, let me back up a bit. The first photon is detected as having arrived at a very particular location on the screen. The second, third, and fourth photons also. They deliver their energy at a single spot, and so they appear to be acting like particles of well-determined position. But check it out. If you keep firing those single photons, you start to see our interference pattern emerge once again. By the way, Veritasium actually conducts this experiment in his excellent series on the double-slit experiment. Really worth a look. This is so bizarre. This pattern has nothing to do with how each photon's energy gets spread out, as was the case with the water wave. Each photon dumps all of its energy at a single point. No, the pattern emerges in the distribution of final positions of many completely unrelated photons. How can that be? Each photon has no idea where previous photons landed or where future photons will land. Yet each photon reaches the screen knowing which regions are the most likely landing spots and which are the least likely. It knows the interference pattern of a pure wave that passed through both slits equally, and it chooses its landing point based on that. It turns out that the photon isn't the only thing that does this. Shoot a single electron through a pair of slits and it'll also appear to land at a single spot on the screen, but fire many electrons and they slowly build up the same sort of interference pattern. This crazy effect has even been observed with whole atoms, even whole molecules. Buckminster fullerene. Buckyballs are gigantic spherical molecules.
So let's stop here with PBS Digital Studio showing that even very large objects like molecules, like the fullerene molecule, can interfere with one another and land with interference patterns. And let's try to see if we can make some arguments about why this whole thing may be happening. Let's take a look at this screen, on our screen behind us. There we are. We're back to my page on the TwoSlit experiment. I'll just scroll down a little bit here. My mouse over here. There we go. So we're on the information philosopher, and we're down on the TwoSlit experiment section. We can't see it quite at this size. I'll shrink this a little bit. So we're looking under the menus at the top of the information philosopher. We're looking at the quantum menu, and we're down here on the TwoSlit experiment. Let me just show you that full screen. So there are many aspects of quantum mechanics that we're going to discuss in this course, but today we're talking about the two-slit experiment. So we quoted at the beginning that Einstein said, Richard Feynman said that this was the most concentrated essence of the problem in quantum physics that cannot be explained in his view, and we must just take the results. He describes it as something he can teach us, he can show you what happens, but he says, do not try to understand it, because, remember, he says, nobody understands quantum mechanics. I'm going to try to take issue with Feynman, and not because my brain is even equal to his, but because I have found in my studies of Albert Einstein that Einstein always wanted to imagine that there was something going on in quantum reality, which he called objective reality. And in that, he wanted to argue that there were things going on which perhaps we couldn't observe, but that they are happening for reasons of deep principles, which he thought remained true of physics, no matter what else experiments were showing us. So let's see if I can bring this page up on another screen, because I can then expand it with us. We'll go to informationphilosopher.com and go down to quantum and look for two-slit experiment with a little luck. Takes me a moment. There I have it. So let me bring this up on a second screen. As you know, it's easier for me to sometimes move the second screen around. And so what I'm going to do is try to tell you why the wave is the secret to understanding the wave-particle duality, and the wave is the secret to understanding what goes through both slits, and it's also the key idea behind Einstein's view of what is going on. I hope to show, as it says here, that the one mystery of quantum mechanics that Richard Feynman is talking to us about is how mere probabilities, which is what the wave function is, can possibly control the positions of material particles. We're looking for the reason why, when the particle goes through the slit, and let's say one particle goes through one slit, what are the probabilities that are determining where it's going to be found? And the answer is, it's those waves in the wave theory. So basically, I've made an animation which shows the opening and closing. Right now we have just one slit open, and we have, with time going by here now, I'm opening the second slit, but very slowly. It's showing up in the background. And now here's our two-slit picture. Now I'm going to take it back to the only one slit open here. Now it'll go through its animation once again, and I'm going to bring that up on the screen behind me so we can talk about this. Let me expand this as much as I can to fill the whole screen, and look at it this way. And we have constructive interference there a moment ago and destructive interference. Here both slits are open, and we see the pattern we saw in those two movies. And here I'm closing that second slit, and now we have just the one slit with the constructive and destructive. You see the beams going out in multiple directions. Now as I open the second slit just a little bit, we get another mixed up picture, and when it's fully two slits open, we see the standard pattern on the back wall, which, as we all remember, happens even when one particle goes in at a time. So here's what I'm going to argue. Here's, by the way, the famous two-slit Thomas Young illustration that was done back in 1802 or so. But we'll go down here. Here's the Feynman lecture, which we'll come back to again later. And let's go back to these two pictures, the single slit Fraunhofer diffraction, and then the dual slit. But then I've built this side-by-side picture that I'd like to talk to you about for a couple of minutes as a way to get past the idea that this is a deep mystery, although it definitely is a mystery. Okay, on the left, I'll come back here. On the left we have the one slit open only. On the right we have the two slits open only. Now, on the top, I've shown a band of light as if you got it out in the form of light. So where the large maximum is where the main light is shown in a spectrum, and very faintly you can probably see the other two side fringes, they're called. Over here we have multiple fringes, and they correspond to those maxima and minima of the function there. So here's our situation. When we have interference patterns with both slits open, even when particles go through one slit. And I'm going to try to say that what Einstein is telling us is that in fact the particle does go through only one slit. And that can be either slit. But when there's only one slit open, the probabilities wave function, the math, gives us this pattern. And this is the pattern which dictates where the particle will land. With this one slit pattern, we get these places on the back wall where we get to see things landing. However, when the two slits are open, the wave function, which is, as I told you, I try to emphasize, is not the particle. It's a theoretical tool, a calculating tool that we use in quantum physics. We solve the Schrödinger equation. It gives us a set of waves. Those waves describe where there's higher or lower probability of finding particles. And now, whether the particle goes through the left slit or the right slit, because the slits are open, the solution to the Schrödinger equation says that the pattern on the back wall is going to correspond to this pattern with multiple bright and dark fringes across the back. So once again, let me kind of repeat what I have actually not found any other physicist telling us, that this is a way to think about it, but guided by Einstein's argument that there is an objective reality. He asked the question, for example, in the context of such an experiment, does the particle have a path in between measurements? We basically fire the particle and heading into the two-slit experiment, and we don't see it again until it lands on the back wall. Now, intuitively, we would think the particle has a path. But the so-called Copenhagen Interpretation of Niels Bohr and Werner Heisenberg is that we should not ask for anything known about that path between the time we fire it and the time it arrives on the back wall, for the simple reason that they wanted to concentrate on what they called observables. And we can observe the measurement of the particle, and we can observe when we fire it off. But in between time, they began to say, don't look here, don't ask what's happening here, as if this was just metaphysical. One of the critical adjectives they used to describe this situation. Quantum reality, they said, is really something we can't know about, and they like to put limits on our ability to even think and talk about these things, instead asking us to focus on only that which we can observe and measure quantitatively. But coming back, let's for the moment imagine what Einstein might have thought about this. And unfortunately, we have relatively little of his critical thinking because he was very unhappy for the most part with the work that was being done by Heisenberg and Max Born and Niels Bohr and Dirac and Jordan and the others who are known as the founders of quantum mechanics. So it's been my work over the last few years to try to read carefully everything that Einstein's been telling us and try to put together a possible argument that he has that would help us think about these mysteries of quantum mechanics. And Richard Feynman tells us this is the deepest of all mysteries. So let's just for a moment imagine that the particle goes through one slit only. Most discussions, including the two we just saw, say, how can it possibly interfere with itself if it goes through just one slit? The next particle, say, goes through the same slit, the next one goes through the other slit. They have nothing to do with one another. How can they interfere with themselves? That's the wrong question. How can a particle interfere with itself? Because what I want you to understand is that there are two things going on here. And much of, I find, of my philosophy and my physics comes down to seeing that where there's one thing going on, you analyze it, there are two ways to see what's going on. The first way is my emphasis on information. The information in the wave function is giving us, allowing us to calculate to extremely high degrees of accuracy the probabilities of where particles are going to be found when we look for them. However, these probabilities are distinctly not the particle, because the values of the probabilities fill the whole space. Remember, Einstein noticed that when the light wave goes off, it goes in all directions. It was thought to be a spherical wave, and here it looks as if these probability waves go off in spherical in all directions. But they are not the particle. Einstein showed that when the particle shows up somewhere, it seems to immediately collapse, because that's the modern term. It seems immediately to have probabilities elsewhere become nil. And that bothered Einstein because, like others following him, he associated this probability in all different parts of space as having some sort of a substantial aspect, which it puzzled him how it is that it could suddenly go to zero here and suddenly be somewhere else. Now, in my thinking in terms, thinking of the probability function in terms of simple math, just a set of numbers that allows us to make predictions about where particles will be found when they are found, the probability wave function is really nothing of a material kind. It is just predictions about the behavior of matter, or energy in the case of light particles. So once again, I find myself in a kind of combination of things going on, something immaterial, something information, often involving randomness, and then something concrete, something real. If you go back to our lectures on free will, we'll come back to another one tomorrow on Tuesday. It's as if the model of free will that I have called two-stage is that there's initially an aspect of free will that focuses on the free part when multiple possibilities are generated, as William James said. Alternative possibilities come to our minds, which are then evaluated in order to make the choice between the alternative possibilities. When the choice is made, then we have an action which involves our body as opposed to just thinking about our alternatives. And although it is not a direct one-to-one match between what's going on here, you can see I'm describing the probabilities in the space as a lot of possibilities. And when a particle shows up at the back screen, that one of those possibilities becomes an actuality. Back up now to our free will model. It's as if the free part of free will is about possibilities, and the will part, of which action we take, is about actualities. Actions are actual choices, decisions to go with one of the possibilities that occurred earlier. Okay, so let me move beyond that diagram, but I have some things maybe we should read here, just so we're really comfortable with what my picture is showing. When there's only one slit open, okay, let me just focus in on the left side for a moment. And here, where we have one slit, you can see that is sort of slightly to the left of center, whereas the two-slit has not one to the left of center, another one to the right of center. But anyway, when there's only one slit open, the probabilities pattern has that one large maximum directly behind the slit, right? You see how that beam going out directly to the maximum behind. Now, if we were to add up the results of some experiments with the left slit open and others with the right slit open, we don't see multiple fringes, because in that case we kept the left slit open only and the right slit open only. So what we get is this picture right here, but we get two of them. So we get, if I take a moment back here, I show you each one of these looks like the right slit, and here faintly the left slit. And what you see is they add up looking like the big maximum and the two on the sides. They do not look like they do not look like the case where we have two slits open. So come back again. Here we're going to see this pattern of multiple fringes on the back side. So let's see what we say about that. When both slits are open, the maximum is noticed now at the center of the two slits. This is quite strange. Where no light might go through the middle, that's where most of the light winds up exactly between the center, between the two slits. And there are more interference fringes. Now, here's the thrust of my argument, okay? When these both slits are open, the probabilities apply whichever slit the photon, the particle, goes through, okay? Because that pattern of probabilities depends on the openness of the slits. It does not depend in any way on the particle coming in. The particle coming in doesn't know whether there's one slit open or two, but the Schrödinger equation of motion, the quantum mechanical calculation of that probability function, is made by examining the boundary conditions in the experiment. Richard Feynman, we'll come back to him again, has always argued that there might be virtual particles sent out in all directions exploring the space in order to establish the probabilities. And I like that very much. And I described that at the bottom here, so let's just jump to that for a moment. Feynman's path integral formulation describes virtual particles that explore all space. This is called the sum over paths theory. And they determine what's called a least action principle of where the particle should go. But in some sense, we could actually say that the probability amplitude wave function has a kind of knowledge about which holes are open at the moment. And if the solution of the Schrödinger equation depends on those boundary conditions, they are different when two holes are open, then we have in one way solved or helped to understand better what's going on, but there remains the one mystery, as Feynman calls it, and that is, how is it possible that these pure mathematical probabilities are influencing a kind of causal control on the atoms or electrons or whatever you're sending through, photons? How is it that this mathematical information only, abstract quantities, numbers that say high probability, not other places that say low probability, how are they influencing on, in a gross, when many of these particles are coming through, how does it influence them to land up in this pattern? That remains a mystery, especially for quantum physicists who want to tell us we understand exactly what is going on by giving us an equation that tells us exactly what happens to every single particle going through. Unfortunately, that kind of deterministic individual knowledge of the motion of individual particles is not available to us in quantum mechanics. Einstein says, it looks to him that this is a statistical theory. It's only telling us probabilities. It's only verifiable by doing large numbers of experiments. We can't know what goes on with an individual particle. But we can, with Einstein, say, we could still say that the particle has a path. And in particular, it has certain properties. It has, for example, conserved its mass. It hasn't been gotten larger or smaller on the way from where it's fired to the wall. It's conserved its momentum. It's conserved its angular momentum. It's conserved its electron spin, or the photon, a spin value as well. And those conserved quantities tell us that there is a continuity of existence, what Einstein called an objective reality for particles. Now, Copenhagen thinkers say, no, don't try to imagine what's going on in this quantum reality. Just be happy with your ability to calculate, and you're able to get exact numbers which are confirmed to be highly accurate, and let's not try to understand what's going on with quantum reality. So my goal with you is to try to think the way Einstein thought about these issues and see whether we can make sense of a kind of objective reality that would make him happy. And I'd really love it if I can restore a certain amount of reputation to Einstein for having given us a really good insight into quantum reality, as he calls it. So let's say goodbye here for now. Hope to see you again tomorrow when we'll be looking into a question of free will. And I'd like to emphasize at that time the idea that it consists of two things: possibilities in the first stage, actuality, a single actuality of choice in the second stage. And so we'll connect it back to my ideas about explaining the mysteries of quantum mechanics. Remember, I cannot explain how individual particles behave, how they know where to land with this picture we have behind us. But en masse, when large numbers of particles are allowed to go through, and it doesn't matter whether they go through one slit or the other slit, because where they land is predicted by quantum physics to be in this pattern on the back wall. And as we just saw in our two videos, that's exactly what we see. I hope as we do this again and again, in coming lectures, you'll get more comfortable perhaps with the idea that there is something going on that at least makes sense, as opposed to our two YouTubes we looked at today that said, this makes no sense. It seems to be nonsensical. There's no way they see where a particle going in can interfere with itself. And I'm saying it really doesn't have anything to do with the particle itself. It has to do with the quantum wave function, which is said to collapse when a particle lands on the back wall. It's merely then that the probabilities don't really relate anymore once you have a measured particle. Now they say it's unit probability that it will be found where it just was found. But to me, the wave function is a kind of overall set of conditions which describe what's going on when the next particle comes in. It will have exactly the same combination of possibilities for landing in different places. And when large numbers of them come through, we get this nice picture, which I show at the top as a kind of bands of light. Whereas if we had only one particle open, we'd be looking at this instead. So thank you very much for being with me today. And we'll take this up again, I hope, my Philosophers and Scientists lecture, which I do on Wednesday, will focus on Richard Feynman this week and look in detail at what he told us about how this was a wonderful mystery. And metaphysics and Einstein will also cover this similar area. Thank you very much. Oh, that